Swayam Prabha. Digital India. Educated India.
Hello. So far, at least in the last lecture, we discussed a mathematical preliminaries for calculus of variations. Today, we jump into calculus of variations. That is to say that we will establish necessary condition or develop the groundwork for developing the necessary conditions for the minimum of a functional. Okay. In normal calculus, you have functions and you have gradients or derivatives. If f of x is a function, df by dx is its derivative, or if f of x, a function is dependent on x and y, then you have partial derivatives, that is dou f by dou x, dou f by dou y. So, dou f by dou x, if you take x component vector, dou f by dou y, you take the y component vector, you get a vector. In 3 dimensions, let us say a function is dependent on x, y and z, then you will have dou f by dou x, dou f by dou y, dou f by dou z. Those 3, if you take as 3 components x, y, z, okay, I am using right hand, so that is correct, x, y, z if you have, then you have a vector that becomes the gradient. In 2 dimensions you have only x and y, so between those 2 you will have a vector based on some magnitude, right. So, that is your vector in 2D. In 1 dimension you just have derivative. That is what we do with functions. But what if you have functionals, which we discussed in the last few lectures? A functional is basically a mapping from a function space to a real number, a scalar, right. Function space, you have a function, you are coming to real number. Now, a functional, that is a real number, if we say that is a minimum, then we have to do some perturbation. We have to see to first order what is a change. For that we need a concept that is equivalent of taking a derivative or the gradient, and that is called variation. So, variation is the derivative counterpart for calculus of functionals. For calculus of functions, normal calculus, you have derivative. For calculus of variations, which is functional calculus, we need equivalent definition, and that is the variation. In particular, that variation has a name associated with a person named Gateaux, and that is what we will discuss, Gateaux variation or a first variation of a functional. So, let us look at the notes that are also available along with these video lectures. If you look at the notes, and I will highlight a few points as we go along today. This concept of Gateaux variation, okay, that is equivalent of derivative. This is the equivalent of derivative that is there in the normal function calculus. Okay. So, what is this Gateaux variation? First of all, it is denoted like this. If j is a functional, we put delta there. That indicates that this thing is the variation of j. Just like we have a function f of x, to write derivative we say df by dx, right. In a similar way we write delta j, okay. That is our Gateaux variation, okay. Now, what does it say? Gateaux variation here of j at x. When I say x, it is actually a function. Ideally speaking, I should have put j as a function of y of x, in which case it will be at y of x. So, if I say my functional j is a function of y of x and its derivatives, right, then del j of y of x will be variation of j at y of x. Okay. Let us not get confused here. In the notes, x is denoted as a function or a vector space that we talked about. Here, if I switch back to y of x, then del j y of x, right, del j y of x variation of j where y is the variable with respect to that function at a particular function is defined in terms of a limit that we will see next. Okay. This is what it is. Now I have changed it back to y of x, not like that. So, we have this functional, we have the function space here, this is the function space, meaning there are a lot of functions in it, that is going to be mapped by this functional j that we have, okay, to a real number space here R. So, if I take any function here, there will be a mapping of a real number here, that is what j does, right. Now, at a particular function, let us say this is my y of x, right. At that particular function, if we want to compute the equivalent of the gradient or what we call the variation, that is defined like this. Okay. So, how is it defined? Its limit some epsilon tending to 0, that epsilon appears here. So, we have taken y of x, if I were to plot it, let us say this is x and I am plotting y of x here from some limits x1 to x2. If I have a function like that, what I am doing here, that I have y of x, but I am adding something, adding h of x. Let us say I define h of x in some particular manner. Okay. So, this h of x that we have, okay, if I add over it, okay. So, if I let us say I have a function like this, my h will be like a perturbation over it, right, that is h, but then I am putting a small value epsilon, dividing by it and making that epsilon tend to 0. So, if this is my y of x, this squiggly line over it is y plus epsilon times h of x, where h of x is an arbitrary thing, you can make it whatever, multiply by a small number because that is tending to 0, epsilon tends to 0, right. That is how Gateaux variation is defined mathematically. Okay. So, let us recapitulate once again that Gateaux variation is now defined at a particular function, just like derivative of a function will be different at different values of x. Gateaux variation is also different at different functions, okay, because now we have function space y of x, that is what is variable now. So, as we vary that for different functions, there will be different Gateaux variations, different first derivatives, okay. Like if you imagine the Brachistochrone problem, between points A and B you join with a curve, that curve will have a variation. If I take another curve, that will have a different variation. So, Gateaux variation depends on the function, but it is also defined in terms of a function h. So, the Gateaux variation we write delta j at some y of x, but also there is h of x. That is what is said in all these notes here, right. So, we have the function y of x, we also take a function that is similar to y of x, but a different one. In fact, this part is arbitrary, this is arbitrary, that can be anything. So, Gateaux variation has embedded in it something that is arbitrary, that we do not have to worry because there is a way to get out of that arbitrariness. Okay. But definition of Gateaux variation involves this h. Whenever we write delta j, later on we may not write y and h explicitly, but it is implied that it is at a particular function and it is with an arbitrary function h, because that h is there, only epsilon is tending to 0, but nothing is happened to h is going to stay on. Okay. Here is graphically what I had said earlier. So, we have y here, that is a solid curve, and then we have y plus epsilon h, which is a perturbed one. Now, we can see how h is over here. Okay. H is also a function like y, only thing is this h is multiplied by a small number epsilon and then added to y. Okay. That is what is a perturbation. between them this shaded region is the kind of variation that at each point. So, at this value of x this is the variation, at this value this is the variation and so forth. Okay. So, we have this variation epsilon h, and epsilon tends to 0. What happens to the functional? So, this is we are plotting only function, but then we have j which depends on y and its derivatives and so on, right, because j, if you take it as an integral, there is an integrand that y and y prime and other things, okay, which is from some quantity x1 to x2. So, that is dependent on y, and how does it change? If y is changed to y plus epsilon h and epsilon tends to 0. When y becomes y plus epsilon h, y prime will become y prime plus epsilon h prime, right. Now, what happens to this j when we make this epsilon tend to 0 is what we want to discuss. Okay. This concept of Gateaux variation, which you defined in terms of limit, also has an analogy in calculus of functions, not our calculus of variations, but calculus of functions, which is to say the directional derivative. Let us say we have a 2-dimensional problem, that means we have function of x and y, right, at a particular point in a 2D domain. Let us say over this text I am going to draw something, right. Let us say this is our 2-dimensional domain. Okay. So, this is our 2-dimensional domain. Inside that, okay, if I take a particular point, there will be a vector gradient dou df, dou f by dou x, dou f by dou y, right. That will be the gradient, but does not tell you how the function will vary in a particular direction that you are interested in. Let us say you take a direction h, okay, that is now h will have, let us say, a component hx in I, that is x direction, hy in the zth direction. If you have something like that, in that direction you want to know if I have a function at a particular point, okay, how does that vary? That is given by this concept of directional derivative, that is defined in this manner. That also with anything that is a gradient is always defined in terms of limit. Here limit epsilon tending to 0, f of x plus epsilon times h. Here h is not arbitrary, although you can ask the rate at which a function changes in any direction. In that sense h is arbitrary, because you can ask in any direction, I can ask in any direction, but h is given, right. In that direction, if you want to know how the function changes, that is given by limit epsilon tend to 0, f of x plus epsilon times h minus f of x divided by epsilon. Here when you put x over bar like we are doing, that means that it has x1, x2, x3, many dimensions the problem can have, f can depend on n variables, right. So, in that case this is the directional derivative. If you look at this and compare with Gateaux variation, you will see that it is similar, right. We have chosen that h of x, we have y of x, we have chosen h of x. You have f of x, we have taken h here, x as a vector, then we have h also as a vector. If we take y of x, then you have h of x also as a function, and that is how you should look at it. That is, if we have a functional and you have chosen a function y of x, then if you say what is the rate of change of that functional with respect to that y of x, that is a Gateaux variation. As it is shown here, direction derivative is also similar. One direction you choose h, what is the rate of change in that direction? It is given by this definition of the directional derivative. So, this directional derivative is the gradient that you take of the function, that is we write delta of f x, right. If I take dot product of that with the direction that you take, because gradient is a vector, this will be the directional derivative of f in h. Okay. So, you take a function and you take its gradient, dot product with h will give you the directional derivative, that is similar to Gateaux variation in calculus of variations. Okay, that is something to remember. Okay. So far we have discussed the equivalent of derivative or gradient in calculus of variation, which is Gateaux variation. Now we introduce a few more terms, something called Gateaux differentiability. We may not need it for this course, but it is good to be familiar with some of these terms. If Gateaux variation exists for all h that belong to x, then x is our function's vector space. Now h is arbitrary, but if you can take any h and take this limit, that is the definition of Gateaux variation, if it exists, then that particular functional j is said to be Gateaux differentiable, some definition. Okay. This limit business is always a tricky thing, because every time if you want to find variation, you cannot go back to limit and work out all these things, that will be inconvenient. While the definition of Gateaux variation we are discussing using limit concept is rigorous and correct, we can use a simpler way of defining that, which is equally correct and equally rigorous, but also operationally useful, meaning that you can do operations with it like we do differentiation without even blinking your eye. Okay. So, that one is what is shown here. This is the same Gateaux variation which is defined in terms of limit. Now it is brought into the realm of ordinary calculus. What do we have here? Ordinary derivative. What are we taking derivative of? We are taking derivative of j y plus epsilon h. Okay. It is a j is a, once you are given y, it gives you a real number. Now we have y plus epsilon h, meaning wherever y is, you replace with y plus epsilon h. Y you are taking there and h is given to you, you have chosen arbitrarily. What is the variable? Epsilon. Now this particular thing we take derivative with respect to epsilon, because that is a function of epsilon, because in Gateaux variation y is taken, h is taken. So what is variable? Which is only this epsilon, right. So we take derivative with respect to that, and then we know in the limit definition we have epsilon tending to 0, substitute equal to 0, and that becomes the Gateaux variation using this h as arbitrary function. This is much easier. This is equivalent to whatever derivative limit that we have defined. Okay. This is operationally useful definition of Gateaux variation. So, because it is useful or convenient, because it has been brought into the ordinary calculus. Okay. So, you do not have to worry about what the form of this j is, you just look at that j as a function of epsilon, because y and h are given to you, you do not need to worry about them, because you are taking derivative only with respect to epsilon. So, treat this as a function of only this epsilon, then we can take normal derivative and then simply substitute epsilon equal to 0 and you have Gateaux variation. Okay. So, this is something that we need to understand really clearly, this operationally useful definition of Gateaux variation. Okay. Now, let us come to this necessary condition, that is what we are after. When the moment we define derivative, we were able to establish the necessary condition for the function that depends on a single variable or multiple variables. Similarly, now for a functional which depends on function, now we establish the equivalent of derivative, which is the Gateaux variation. So, we can establish necessary condition now, okay, for minimizing the functional. All right. So, like we had discussed in the case of functions, that somebody tells me a function is f of x, and when I want to minimize at a particular x star it is a minimum, then what do I do? That at x star we perturb it slightly and then say that to first order there should not be any change, because first order change can be positive or negative. So, the first order term can become positive or negative, and we cannot say anything about that function being minimum there. So, we say first order term should be 0. Similarly, here we say that first order term should be 0. Our starting point is first say if y star, that function, were to be a minimum, then after perturbing. So, we have the functional as a function of y star, but then we will have another one after perturbation y star plus epsilon times h. The difference of this, if really j y star is the minimum value, any other perturbation should be larger. So, we say j y star plus epsilon h minus j y star should be greater than or equal to 0. That is the definition of a minimum. And then local minimum when we say, right, then we say for sufficiently small epsilon, what is that change? That is, how do you expand this, right? This is, we know, we can compute it. How do you expand this with this thing? If you think about that, then we can write like a first order term, right. So, what first we are saying is that we take that whatever we want, right. So, when we expand it, there will be a 0th order term. So, what we have, what is encircled now, we have a, we divide into 0th order term which will be j y star itself, right, and then we will have the first order term, and then we will have second order and others, what we write O2, right. So, j y star cancel. So, it all depends on this thing, right. So, that is what we will get to and show that this is nothing but Gateaux variation. So, what we do here is that for epsilon greater than or equal to 0, we want the numerator part of it to be greater than or equal to 0. If I divide by epsilon, when epsilon is greater than 0, this is true. When epsilon is less than or equal to 0, this portion will be less than or equal to 0, because the numerator is positive, denominator is negative or non-positive, it will be less than or equal to 0. If we let epsilon tend to 0, this one and this one, here we are saying epsilon is greater than 0, here epsilon is less than 0, that is we are approaching 0 from the right side, that is epsilon greater than 0, and then second one, here we are coming to the limit from the right side, and here it is the left side, we are coming this way. This says greater than or equal to 0, this less than or equal to 0. What should it become? It should become greater than or equal to 0, right. That is nothing but our Gateaux variation that we have, that definition of Gateaux variation, which is to say that first order term is equal to 0, because derivative being equal to 0 is the first order term for normal functions. For functionals, Gateaux variation is equal to 0. That is how we establish our necessary condition. You see that we still have that arbitrary edge that we will get rid of later on, which will be in the next lecture. So, if you want to state it as a theorem, the necessary condition for a minimum functional is this, that is Gateaux variation is equal to 0. Okay. And there is another concept called Frechet differential, okay, which is a little bit, I would say, more advanced than Gateaux variation, because if you look at this definition, okay, in this definition, this dj y h, if we compare this with Gateaux variation, where instead of using d here, we had put delta like this, right, here it is just d. So, this dj is Frechet differential, okay, that is this Frechet differential, okay, that is defined not in terms of epsilon, it still uses h, okay, but we are putting the norm of h in the denominator, making that norm of h tending to 0. If we do that, if this is equal to 0, that is limit norm of h, an arbitrary function h of x, there is a norm that we had discussed earlier. When that norm tends to 0, the numerator j y plus h minus j y minus dj y h, Frechet differential, divided by norm of h, if that limit is equal to 0, then this dj is called the Frechet differential. Okay, it is a little bit more rigorous, because we are involving the norm of h and not just taking epsilon variation. Okay. So, this has some interesting properties, basically to say that if you look at this, this is a 0th order term j y plus h, that is I have a y and I am adding another function h, then there is a perturbation in the functional value j, that is a 0th order term, and then we have this which is the first order term, is the first order term, right, and then there are higher order or the error term. So, the third one that we have, okay, this third one is the error, always be error like a Taylor series expansion equivalent here, right, that is Fresher differential. Okay. And this error tends to 0 as h tends to theta. Theta here is the null function. Every function space will have a null function like a 0 function. When this h, that is arbitrary, tends to the null function, this error tends to 0. That is what this says. There is interesting properties which you can go through in the notes that is going to accompany this video lecture. For example, this Fresher differential is actually linear, meaning that you can do operations like that. So, basically linearity, it is a first order term, it is linear, understand that much. Okay. And there is a relationship between Gateaux variation and Fresher differential. The relationship is that when Fresher differential exists, that is equal to Gateaux variation. Okay. That is what it says. And there is a way to prove that, and you can go through this in the notes to see why that is the case. Just a systematic argument to say when Fresher differential exists, that is equal to Gateaux variation. But what we need for our purpose is only Gateaux variation, but we are just mentioning some of these so that you are familiar with them. Okay. Some operations that you can do with Gateaux variation which we are going to discuss later. So, when you have a functional whose integrand depends on y of x and also y prime of x, we can actually do this, d by d epsilon of j y plus epsilon h. If you do and treat epsilon as a variable, that is a variable, then you are doing this, right, d by d epsilon of f of where y is, you have substituted y plus epsilon h, where y prime is, you are substituting that with y prime plus epsilon h prime. You take derivative. Okay. Derivative use normal calculus rules for differentiation. So, here f is a function of y plus epsilon h. So, you have to do the chain rule. You take derivative with respect to y plus epsilon h and then take derivative of y plus epsilon h with respect to epsilon. Okay. That is what we are doing this operation. So, I am taking derivative with respect to y plus epsilon h, and then this is derivative of y plus epsilon h with respect to epsilon. That is a chain rule. Okay. Similarly, taking derivative with respect to y prime plus epsilon h prime, taking derivative of y prime plus epsilon h prime with respect to epsilon, that gives you h prime. Okay. So, the variation, if you want to just write it like that, you can do it. Some people call it delta rule or delta property or delta differentiation, that is just a way of remembering, but this lecture you should pay attention because it comes from a concept of Gateaux variation. Otherwise, if you just know how to write this like that, that is good enough. You are taking dou f by dou y to h, dou f by dou y prime h prime. Similarly, if you have y double prime in the integrand, then there will be dou f by dou y double prime h double prime. Y triple prime, if we have, this will be dou f by dou y triple prime times h triple prime, but that is following from the Gateaux variation, especially the operationally useful definition that we discussed. So, these operations you should be comfortable with. Okay. There is another very interesting concept of variational derivative. We discussed Gateaux variation and Fresher differential. Now, the third one, variational derivative, okay, which is very important, and in fact, this is how the history says Leonhard Euler had derived his equations for necessary condition. Okay. What he did, again you should read the notes to understand the details, but he had simply used the notion of partial derivative. Okay. How did he do that? What he did was, if we look at this graph, we have an unknown function. Okay. You pretend that it is not unknown function, you are discretizing like here x0 to xn, and you say the heights are not known. If I say x0, I do not know what that height is, x1 I do not know what that height there is, I can call it y0, I got y1, those heights are not known. If I take another point x2, I do not know y2 and so forth. He basically discretizes. When it discretizes, the integration that you have in the functional becomes summation, right, and then derivatives are represented in terms of these discrete values as a finite difference one. So, everything is now in terms of y0, y1, y2, which becomes finite variable optimization. That is the kind of thing he had taken. So, you have the derivative expressed in terms of finite difference values in terms of the unknown y's, y0, y1, y2 and so forth. He takes these partial derivatives, makes it equal to 0, okay. It is a very elegant derivation. So, he takes it all with partial differentiation alone and establishes a condition, okay, that we today call Euler-Lagrange equation, okay, which we will do in the next class using the Gateaux variation concept and all of that, but Euler had done this very effectively using only partial derivative concept by discretizing and making that limit tend to 0, then you will get what is called. But this particular quantity today we call it variational derivative, which is nothing but Euler-Lagrange equation. When I say equation, I say that there should be equivalent, something should be equal to 0, we say this is equal to the necessary condition, okay. But this quantity that we write, this delta j by delta y, see today we discussed delta j which is Gateaux variation, dj which is Frechet differential. Now, we have third one variational derivative which we derived for the case of an integrand that depends on y and y prime, but later in the next class you will see whatever we get this Euler-Lagrange equation, the left side of it equation will have a right side and left side. In the case of Euler-Lagrange equation, right side is 0, whatever is the left side is nothing but this variational derivative. That is something that we should remember because this variational derivative, again if I look at the first order change, that is again given by this delta sigma here is the perturbation. Let us say I have a function at one particular value, if I raise it, that function like that, this thing, okay, is delta sigma, which we will be needing when we discuss constraints in the calculus of variations framework, okay. So, to sum up, today we discussed three things: Gateaux variation and then Frechet differential and variational derivative. Gateaux variation is needed for us in all the things that we do in this course. Frechet differential is just a concept that you are familiar. If you do not understand, it is okay, but if you take a function analysis class, you will be needing that. Third is the variational derivative, which we need when we discuss how to incorporate constraints in calculus of variations, okay. Next class we will actually derive these Euler-Lagrange equations, which become the foundation stone for everything else that we will do in the rest of the course. Thank you.